And today I am going to discuss about the power factor and effective values. First we will define these two terms, power factor and effective values. What is power factor and what is effective value? And later on we will discuss the significance of these two terms, power factor and effective values. So power factor is defined as a figure of merit which measures how effectively energy is transmitted between a source and a load network, and it is defined as the ratio of average power to the apparent power, or you can say the true power to the apparent power. True power which is consumed by the load, and the apparent power is supplied by the utility. So try to understand this with this simple expression: kilowatt equal to kVA into cos phi. So this cos phi is your power factor, and this kilowatt is the load property, and this kVA is the supply, or you can say the utility. So kVA is the power supplied by the utility, and kilowatt is the power consumed by the load. So this is called your active power. This is called active power, or you can say the average power or true power, and this is called your apparent power. So it is the ratio of true power to the apparent power. Significance is, so suppose if the power factor is, say, it is unity, then kVA is equal to kilowatt. So if the power factor is unity, it means whatever the energy supplied by the utility is consumed by the load. So there is no losses in between the supply of the system and load network. This is the ideal condition, but in the practical case there are some losses. It means power factor is not unity. So, and the another term is effective values. So what is effective values? Effective values of a periodic current IT. Periodic current means it may be sinusoidal, it may be non-sinusoidal periodic, is defined as the constant value of the current which will produce the same power in a resistor as is produced on the average by a periodic current. So this is the definition of the effective power. So power in a resistive load or in a resistor due to the current, constant current is given by P is equal to I square R, and in the sinusoidal steady state the average power in the resistor is given by this is the expression for average power if the input is your periodic. So this is the average power, half Im square R. So since both the power P is equal to P average, so it means I square, or you can say I is equal to Im upon 2 upon root 2. So this is called I effective. So I effective is nothing but it is the ratio of maximum current divided by the under root 2. So, equating we get this. So, this is the average power. Similarly, we can define V effective. So, V effective is Vm upon root 2. Similarly, we can define the V effective and I effective. So, these are the effective values of current and voltages. So, it is the maximum power divided by under root 2. Now, discuss the significance of power factor. Suppose if the load is your purely resistive, but the supply is non-sinusoidal periodic. Say it is like this. This is your sawtooth. It is periodic, but your non-sinusoidal. Say T, 2T and so on. So, in this case the current harmonics are in phase with and proportional to the voltage harmonics. So, it is non-sinusoidal, it will have the harmonics, fundamental as well as harmonics. So, in this case the harmonic currents generated by the non-sinusoidal voltage means harmonic voltage will be in phase with and proportional to the voltage harmonics, and as a result all harmonics result in the net transfer of energy to the load. So, current harmonic magnitudes and phase are given as. So, In is equal to Vn upon R. So, suppose for the fundamental it is V1 upon R, for the second harmonics V2 upon R and so on. And this theta and phi and they are equal because they are in the phase. So, they are in the phase, so phase angle is the 0. So, in this case this is your power factor is unity. So, RMS value is, so RMS value in case of input is non-sinusoidal, it means it will contain the harmonic voltage, and due to the presence of the harmonic voltage there will be the harmonic currents in the system. So, this is the VRMS is the V0 square plus n is equal to 1 to infinity Vn square upon 2. So, V0 is DC value, you can say the DC value and V1 is fundamental n is equal to 2 is the second harmonics, n is equal to 3 third harmonics and so on. So, this is the expression for VRMS or V effective in case of load is resistive and the input voltage is non-sinusoidal. Similarly, we can calculate the RMS current. So, RMS current is, this is the RMS current, we can write in terms of the voltage. So, it is 1 by R RMS voltage. So, IRMS is equal to VRMS upon R. So, what is the significance? So, presence of harmonics in a signal always increases its RMS value. Okay. So, we can see that IRMS is increases, due to increase of the IRMS, I square R losses will be increased. So, in the case where the voltage contains only fundamental while the current contains harmonics, look at, then the harmonics increases the RMS value of the current while the average power remains unchanged. So, average power is P average is V1 upon I1 upon 2. So, both this is the fundamental voltage, this is the fundamental current. If the fundamental voltage and current both are present, then we can get the power to the load. Okay. If suppose second harmonic, V2 is 0, but I2 is present, then power will be 0, no transfer will be power to the load. So this is undesirable, and because harmonics do not lead to net delivery of energy to the load, and they increase the losses. So I square R losses will increase in the load. So if both the components of the voltage and currents are not present, then it will not take part in the energy transfer. So this is the significance of the presence of the harmonics in the system. So I square R losses will increase because IRMS will increase. Now look at the another example. If the load is your dynamic and nonlinear, but the supply is sinusoidal. So sinusoidal voltage means all the harmonics are absent. So V0 is equal to 0, there will be no DC component, V2 is equal to 0, V3 is equal to 0, only fundamental will be present. So in this case, this is your DC value, this is the DC value, this is your DC value, and this is your second harmonics, and this is your third harmonics. So all the harmonics are absent because the supply is your purely sinusoidal. So the harmonics in IT do not result in transmission of net energy to the load because V2 I2 0, product of this is 0 because this is 0, so energy transfer will be 0 due to the harmonics. So in this case average power is V1 I1, this is the fundamental component, and this is the phase difference between the current and voltages. So however the harmonics in IT do affect the value of the RMS current. So this is the average power, but IRMS will increase due to presence of harmonic currents. So RMS is this is your DC value, and N is equal to 1. So I1 upon 2 summation I1 square upon 2 plus I2 square upon 2 plus I3 square upon 2. So we can see that this is the fundamental and this is your harmonics component. So IRMS is increasing, this value is increasing. So these components I2, I3, I4, I5, they will not take part in the energy transfer. What will they do? They will increase the RMS value, and once the RMS value increases, it will increase the losses in the system. So harmonics causes the load to draw more RMS current from the source, but no more average power. Okay. So it causes additional losses in the series resistance element R series, and also presence of dynamic load, the resistive element which cause the phase of the fundamental component of the voltage and current to differ, also reduces the power factor. The power factor will go down. If the power factor will go down, so we can see that for the same kilowatt demand, the KVA, for the same kilowatt load, the kVA demand will be more if the power factor is low. So, the cos phi 1 minus alpha 1 term is the average power. So, this component will take only part in the power transfer. So, it becomes less than unity. So, the power factor becomes less than unity. So, however, the RMS value of the current does not depend on the phase. So, shifting the phase of IT with respect to Vt reduces the average power without changing the RMS voltage or current, and hence power factor is reduced. So, this is the conclusion of this. So, power factor is, come to the basic, power factor is the ratio of average power to the Vrms and Irms, means active power to the apparent power. We have calculated active power. Active power is Vm by root V1 by root 2, I1 by root 2, cos phi 1 and alpha 1. This is the angle between the current and voltage, and this is V1 by root 2, which is Vrms. So, it is Vrms and only one component, because supply is sinusoidal. And this is the RMS, this is your IRMS. So, IRMS current will increase. So, this is the average power, this is the apparent power, and we if we segregate, so the power factor is, this is, there is one factor I1 by root 2, fundamental component of the current, this is I1 by root 2, and this is your IRMS, this is your IRMS. So, what is this? This is your IRMS, because this and this cancel out. So, this is IRMS, and this is the angle between the fundamental voltage and current. So, what we conclude? So, this is called your distortion factor. This is called distortion factor, another term, and this is called displacement factor. Because phase angle is not 0, phi is not 0, so it is called displacement factor. So, power factor is the product of two terms, one is the distortion factor, or you can say the harmonic factor, and another one is the displacement factor. So, we can write power factor equal to distortion factor, and this is the displacement factor. Distortion factor is also known as THD, total harmonic distortion. We calculate the total harmonic distortion if the load is nonlinear, or if the supply is your nonlinear. If the load is your purely linear and supply is nonlinear, then it will also contain the harmonics due to presence of the harmonic voltage. If the load is your nonlinear and supply is nonlinear, supply is purely sinusoidal, then due to the presence of nonlinearity in the load, it will also generate again harmonic currents. So, in both the cases, harmonic current will be developed in the network. The question is whether this harmonic currents will take part in the energy transfer or not. If it is not taking part in the energy transfer or active power, then it is generating lot of heat in the system. So, it will heat the system. So, we can conclude the significance. Suppose again basic kVA cos phi. If the cos phi is low, So for same kilowatt load, kVA demand will be more. kVA demand will be more to match the load rating. To match the load rating, if the power factor is low, then kVA demand will be more. Once the kVA demand is more, then this current will increase. Current will increase. Increase means RMS value of the current will increase, then the losses will increase. So if you are using devices which causes the low power factor, the utility will penalize you, okay, because these losses current will increase, there will be the losses in the system, in the cables, in the transmission line there will be the losses, and if you are using the low power factor devices, inductive loads, then the power factor will be low, it will kVA demand will be more, so utility will going to penalize you. So this is all about your this two topics, power factors and effective values. So we discuss what is power factor, what is effective values, and what are their significances when the load is linear or non-linear, or supply is sinusoidal or non-sinusoidal. So we stop here. Thank you very much. Jai Hind.